Welcome back. As we were discussing in the last class, today we will be discussing the Stille reaction. Stille reaction is the carbon-carbon bond formation reaction where organohalide is used in conjunction with organotin reagent. The moment one is talking about tin reagent, there the first problem that comes into mind is how this is going to be industrially relevant, because industry does not want to use the tin reagent. Indeed, that is the one and only problem that we have with Stille reaction. Industry does not like it, medicinal chemistry people does not like it. But then why Stille reaction is so popular? Because it works beautifully almost for everything. So, academician is going to like it. Academics favor it is the Stille reaction, mainly because of the fact every functional group works beautifully. Usually very little problem is associated with the Stille reaction, and therefore, also it is one of the carbon-carbon bond forming reaction which has seen most use in natural product synthesis. The big molecule synthesis we see are quite useful under the Stille reaction condition. So, today we will discuss the Stille reaction, some example of the Stille reaction. As we have said, the drawbacks of the Stille reaction is the industrial use, medicinal chemistry use is not really viable. Nonetheless, it remained very popular in academia as well as in natural product synthesis. Okay, let us look at Stille reaction. So, you have Rx reacting with R prime SnBu3, for example, palladium 0 catalyst. In presence of additive, we get R prime as the product. So, this is very widely used in natural product synthesis. But R3SNX is toxic, of course it is. So, there is problem in medicinal chemistry, problem in industrial use. Therefore, although this is problematic, what we see these Rx could be aryl, vinyl and alkyl, all different variation that you can think of that is good with these reactions. And this R prime over here can be once again good for aryl, vinyl, alkyl. So, that is quite interesting, and this reaction is often air and moisture stable. These reagents, particularly tin reagent, are air and moisture stable. So, that gives the access, or that gives the possibility that it can be used quite widely for academia. The reagent we do not have any problem in dealing with, we can pretty much use under quite normal condition, and therefore, the very challenging reaction, let us look at one such example where it is a challenge to synthesize the product, but Stille coupling can deliver the product where a diacyl unit is involved. Examples. Now, we have this chloride, diacid chloride, and one is interested in using this tin reagent. under THF at room temperature, even the desired product, that is the ketone product, diketone product, one could imagine. That is beautiful demonstration of this reaction. This gives 62% yield of the product. Another interesting point could be, of course, if we are to synthesize a product such as these, any of these are of deactivating. These coupling partners are very tough one, because you have electron rich substituent, electron rich as well as aryl chloride. As you know, the reactivity pattern is iodo is most reactive, then bromo, then chloro. If you are reacting it with RSNBu3, even this reaction works quite beautifully in presence of palladium p-butyl 3 cesium fluoride under 100 degree C condition. We get the desired product. For example, here you different R group you can have. R, if R equal vinyl, you get 83% yield. Allyl, you can get 87% yield. Allyl, phenyl 94, N-butyl 82. For these reaction, therefore, you have different alkyl partner or different R group ranging from vinyl, allyl, alkyl, aryl. All those can give very good yield of the desired product. Well, that is quite interesting. Irrespective of the coupling partner, we get very good yield. On the other hand, you can take the toughest possible substrate. One such substrate we have shown, that aryl chloride. Again, the chloride coupling partner are the most difficult one, because the oxidative addition is the slowest with aryl chloride. On top of that, with aryl chloride, if one has the electron rich substituent such as methoxy, it is even more difficult. Still, under the Stille reaction condition, we can get those coupling going in quite good yield, and under the standard palladium catalysis, we can get this product in quite high ratio. Let us look at some more example of the Stille reaction, where we will be able to appreciate the efficiency of such reactions. So, we will look at more example of these. RSNBu3 we are using. R equals could be butyl, usually no choice but butyl, but anyway, let us look at the carbonylative version. Now, as we were looking at the Suzuki reaction, for Suzuki reaction we have also seen between two coupling partner, namely aryl boronic acid or any boron partner, as well as aryl halide. If we are doing this reaction under the CO atmosphere, we were able to get carbonylative Suzuki coupling between one coupling partner and another coupling partner. There was a carbon monoxide. Similarly, for Stille reaction also, we can have two coupling partners. One is halide, another is the Stille reagent. If we are doing this reaction under carbonylative condition, that means carbon monoxide in presence of it, we can get the corresponding ketone product. Most importantly, even both the coupling partners are alkynyl substituted or alkynyl derivatives, still we can get this product quite efficiently. Let us look at one such example, where we have styrenyl halide reacting with SnBu3. Again, we have another alkynyl partner. We end up getting the product that we are looking for, CO in between the product. This can be done at room temperature using catalytic amount of palladium PPH3 to Cl2. Well, That is again once again very interesting. By this process we can synthesize a ketone, any desired ketone can be synthesized by using this Stille coupling. You can have diaryl ketone, you can have aryl alkyl ketone, you have alkyl alkyl ketone, you have alkenyl alkenyl ketone in between, right. Another interesting thing could be, can we synthesize aldehyde by this method? Well, as it turned out, one can, starting with alkenyl halide or even aryl halide with a heterocycle coupling partner and the tin reagent with tin hydride as a coupling partner. Instead of an alkyl, now we have a hydride reagent to transfer, and therefore, we can get the corresponding aldehyde. So, that is once again a very attractive reaction. Not only ketone, aldehyde can be synthesized by utilizing this technique. Let us look at that. We have, for example, one of the most troublesome coupling partner is this thiophenyl iodide at 3 position with tin reagent at HSNBU3 with palladium tetrakis once again to rescue 45 psi CO, we can get the corresponding aldehyde. Well, because this hydride is coming from this tin reagent, right, tin hydride, tributyl tin hydride reagent that is used. So, what we have just seen that not only ketone, aldehyde can be synthesized quite beautifully. Let us look at one of the little complicated synthesis which at a glance from the product perspective it could be complicated, but from Stille perspective this is a simplest reaction of all, where we will undergo oxidative addition, insertion into an unsaturated molecule and finally coupling with a Stille condition or Stille tin reagent to give the desired product. So, we will see a sequence of events happening to give a desired product which otherwise would have been very difficult to synthesize under normal condition. Let us look at application, further application of such reaction. So, oxidative addition, beta migratory insertion and cross coupling all are happening in one pot at one stage. So, the substrate for this reaction is a little bit decorated one. So, the bromo coupling partner with it O benzyl and you have an allylic alcohol O protected one, and you want to react it with Bu3SN, this alkyne reagent. Well, that is of course an alcohol protected version. Now, what would be the product if you are adding catalytic amount of palladium PPH3, palladium tetrakis in this case? As it turned out, this gives you a cyclized product. So, oxidative addition will occur first at the alkenyl halide center. That palladium intermediate will insert in a beta migratory fashion with the dangling alkyne intramolecular fashion. Subsequently, it will react with the tin reagent. Let us look at the product formation first and then we will draw the mechanism stepwise. So, the product that we get in this case is the one where we have SiR3 alkenyl and we have OBN and OSiR3. Okay. So, that is the product formation. How is this product formation happening? Of course, overall you have this alkyne sitting over there. The first step would be the oxidative addition into the alkenyl halide, oxidative addition over here to give the palladium bromide intermediate, and this then insert into the alkyne to give you palladium bromide. Now, this coupling partner at this site, so then over here as you can see over here, then it reacts with the tin reagent to give you the final desired product. So, that is quite interesting, I thought, overall for these processes. And then therefore, we have a substrate in this case where we have alkynyl halide perfectly positioned in front of an alkyne, oxidative addition into the alkynyl halide, insertion into the alkyne, and subsequently that in situ formed alkynyl halide will react with the tin reagent to give you the final product. That is a powerful demonstration of the Suzuki reaction where sequentially oxidative addition, beta migratory insertion and the Stille coupling finally is taking place. Overall then, what we do have a Stille coupling, it works beautifully for academic purpose, but it is not a great choice for industrial purpose because of its toxicity. Any given reaction you can think of, perhaps you can think using the Stille coupling if it is not of medicinal use. Stille coupling is used quite beautifully and quite extensively in academia. In selective cases in industry also it can be used. Now, let us look at the problems that is associated with the alkyl partner. So, the coupling reaction has a number of problems. One such problem is incorporation of alkyl partner either in the form of electrophile or nucleophile during the reaction. Let us look at if you have alkyl halide, what type of problem one may associate during the reaction and why a desired product formation may be hampered because of the nature of the alkyl halide. We have alkyl electrophile. Now, alkyl electrophiles, for example, if you have alkyl halide and you want to react with R prime M, any catalyst you want to put and you want to get that one. The problem, the first problem that one associates with this is if it reacts with palladium 0, it gives of course the palladium bromide oxidative addition complex, but from the beta position alpha beta position, this beta hydride elimination that is intramolecular reaction. Before this one proceeds for reacting with R prime M to give the desired product, a side reaction which is intramolecular, and that is where it is very difficult to prevent, can proceed to give the palladium hydride and bromide, right. Well, if that is happening, one would expect that corresponding problem of getting the desired product. So, olefin will be formed from this reaction, not the desired product, or good amount of this beta hydride elimination product can jeopardize the formation of the desired coupling product. Well, this is why we see that alkyl halide are challenging partner for these coupling reactions. One way to solve this problem is to discourage the beta hydride elimination. Of course, you have to have the alkyl partner, you want to use the alkyl partner. So, changing alkyl partner to aryl or something else does not solve the problem because you want that desired product. In order to do that, if one is using a bulkier ligand, then due to as you see for the beta hydride elimination, coordination number is increases, but if it is a bulkier ligand already present with the metal center, then beta hydride elimination may be discouraged to some extent. So, this is where a bulky ligand can be good. Of course, ligand has to be electron rich, but usually phosphine ligands are electron rich enough, and therefore, oxidative addition may not be a problem for the phosphine ligand, but the bulkiness can be beneficial for preventing the beta hydride elimination. Let us look at those alkyl coupling between the between alkyl halide and the alkyl boronic acid partner. Solution to this problem is the Suzuki reaction solution with palladium, and that is using hindered or phosphine reagent. If you are taking R prime CH2 CH2 Br, we have seen the other coupling partner as this one. Overall, if you are reacting it with catalytic palladium acetate in presence of PCOI3 and potassium phosphate as the base, hindered and electron rich, this triflyne phosphine tricyclohexyl phosphine is hindered and electron rich, that is crucial, and that is why we get the product, the alkyl product, corresponding alkyl product in very good yield. Well, that is a very good reaction where we see that alkyl halide is used in conjunction with alkyl boron reagent to give you the corresponding sp3 coupled product. Although this is a successful reaction, still it remains one of the most challenging problem that sp3 coupling is not really that the easiest of the coupling partner that one can think of for this reaction. Many recent developments has solved this issue to some extent, mainly the very beautiful contribution and important contribution by Professor Greg Fu's lab, which has given not only this coupling aliphatic coupling, even the asymmetric version of this reaction has been solved quite beautifully. But by this way, this PCOI3 is good for, let us say, aliphatic partner, but they may not be, or they are usually not good for secondary or tertiary halide, because for secondary and tertiary halide we have whole bunch of other problem to deal with along with this reaction, where we see that sp3 primary center is working, the secondary center will not be happening oxidative addition because it is hindered aliphatic halide may be preventing the oxidative addition, because usually oxidative addition is occurring under SN2 reaction condition, right. So, the backside attack could be problematic. Let us look at one such problem where SN2 reaction for oxidative addition is going on, and then look at the example with that. So, the previous reaction works well for the primary, but secondary and tertiary PCOI3 does not work that very well. Let us look at one of the example. Mechanism of oxidative addition, usually it is a SN2 reaction. Okay. The type of substrate that we would like to demonstrate for this, to prove that it is a SN2 reaction, is where you have deuterium labeling into the substrate. So, these are trans to each other, and the reagent that is working or we are interested in doing is the Suzuki coupling partner, aryl boronic acid or aryl boron reagent, and in presence of palladium 0 catalytic amount and PR3 in presence of base such as sodium hydroxide and heat. What we get in this case is tert-butyl, phenyl and deuterium. Deuterium, you see, it is the one which is the major product. The stereo center over here, as you can see over with respect to here, is opposite. That means this is indicating that this is a this is a SN2 reaction that is happening during these cases. So, what we have seen in this particular example is we have alkyl halide. Alkyl halide is working with a boronic acid reagent or aryl boron reagent to give the desired product, but the alkyl partner is having two deuterium, one at alpha position, the another as beta position. We started with the one of deuterium at the alpha position. In the product, what we see that it is below the plane, that means a SN2 reaction is happening during the oxidative addition reaction, because the reductive elimination is usually not going to be it is concerted process, it is not going to change the geometry or it is not going to change the stereochemistry at the partner. So, alkyl partner stereochemistry is changing, that demonstrate that for alkyl halide it is a SN2 reaction that is happening with the metal center. Therefore, one could imagine that it will be problematic for the secondary and tertiary halide to undergo the SN2 reaction, because backside attack is going to be difficult for secondary and tertiary halide. Therefore, what we have seen so far is, although for primary halide these reactions could be possible, a coupling reaction could be possible, but secondary and tertiary coupling partners remained one of the most problematic issue in the cross coupling reaction or carbon-carbon bond formation reaction. In the next class, we will discuss some of those issues, not only that, the asymmetric version of those issues, and some examples by Professor Greg Fu's lab, who has contributed immensely to solve these problems. In today's class, therefore, we have discussed why alkyl halide is a difficult coupling partner, because it gives you the side product in the form of beta hydride elimination. How to solve it? We can solve it by having tricyclohexyl phosphine electron rich bulky phosphine that can give, but it is not a generalized solution for every aliphatic halide, because for aliphatic halide it is a SN2 reaction condition that is predominant for this reaction. Therefore, SN2 reaction cannot tolerate secondary and tertiary substrate, and thereby we have a problem to deal with. In the next class, we will see how to get around this problem even with this alkyl halide. What is the strategy? What should be the metal that we should use, perhaps not palladium, some other metal to use, so that we can change the reaction mechanism itself, and thereby we can introduce secondary and tertiary halide. Even perhaps using a chiral ligand can give the stereo center that will be generated during the carbon-carbon bond formation process. We will discuss all those in the next class. Till then, you keep reading about these carbon-carbon bond formation reaction. Bye bye.